Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to talk about Dalton's law of partial pressure, which is actually kind of simple. It just means that the sum of all the individual pressures is equal to the total. So if I had three pressures, I would just add them up together, and that would give me the total pressure. So let's pretend we have a vessel, okay, or a container that is 2.8 liters in size. And inside that, we're going to place 5 grams of carbon dioxide and 3 grams of neon, and we're going to hold it to a temperature of 300 K. The three questions that I'm going to have, okay, is what is the pressure that comes from just the carbon dioxide? And we would call this a partial pressure, okay, a partial pressure of carbon dioxide. I also want to know the same thing for the neon. What is the partial pressure of the neon? And according to Dalton's law of partial pressure, if I know both of those pressures, I can add them together and I can figure out what the total pressure is. So I guess the task in this particular problem is to figure out what's the partial pressure of carbon dioxide, what's the partial pressure of neon, and then simply add them together to get the total pressure. So let's get right into it. What we're going to do first is we're going to use PV equals nRT. This is always a pretty good starting spot for doing gas problems. And if I want to find the pressure, I'm going to have to divide by volume on both sides. So this is going to end up looking something like this as a problem. Now, I need to have the moles, and I don't have them. I only have the grams. So the first thing I'm going to do is convert these grams into moles. So I'm going to convert the grams to moles. So I'm going to add up 2 oxygens and a carbon, and that's going to total 44 grams per mole. And when I do that math, the carbon dioxide comes out to be 0.1136 moles of carbon dioxide. And I'm going to do the same thing for the neon. I'm going to convert the grams to moles, and the molar mass for neon is simply 20.2 grams per mole. And I got that off the periodic table. And when I do this math, I find out that the neon is 0.1485 moles of neon. Now, I kind of want to pause here and ask you, which one do you think is going to exhibit the more pressure? Okay, the carbon dioxide is 5 grams, but that's only 0.1136 moles. The neon is 3 grams, okay, but it ends up being more moles, okay, because when you consider their molar mass, you know, it looks like there's more moles of neon than there is carbon dioxide. So when I'm done with this problem, I'm expecting to have more pressure from the neon than the carbon dioxide because there's more moles of it, okay? You don't look at the grams, you're going to look at the moles. So I'm going to plug these values in for N, okay? So I'm going to leave the N kind of blank. And then the R is equal to 0.08206, and that's ATM liters over mole Kelvin. The temperature is 300 K, and that's all over the volume of 2.80 liters. Okay, so what I would do is I'm going to plug in my carbon dioxide moles in right here, 0.1136. times this, divided by this, to get the partial pressure of the carbon dioxide. And when you do that, you get a partial pressure of the carbon dioxide as 0.999 ATM. So basically 1 ATM. Okay. I'm then going to plug in my moles of neon, which is a greater number. So I'm going to get a greater number than 0.999. Okay. So when I plug in the 0.1485 times this, divided by this, I'm going to get the partial pressure of the neon. Okay, and when I do that math, it comes out to be 1.31 ATM, which is a greater number. Okay, and then finally, if I want to get the total pressure, I'm just going to add both of these together. So 0.999, which is basically 1, plus 1.31 is going to give me a total pressure of 2.31 ATMs. Okay, so this is a simple problem how to get partial pressure. Okay, now there's going to be another piece to all this. Okay, what if, okay, they didn't give me the volume and temperature? Okay, and what instead they just gave me the total pressure. Okay, of the system. So I'm going to do a particulate diagram, and then we're going to come back and investigate this type of problem where you have to figure out the partial pressures from a total pressure and never ever have the volume and temperature, which looks like it's needed to solve that problem. Okay, so let's take a look at a particulate diagram problem, and then we'll come back to this problem. Okay, so I'm going to do this particulate diagram kind of like over here. Let's say I have this container that's filled with X's and O's, okay, and I'm going to put 3 X's in here, and I'm going to put the rest O's, so that's like 9, right, for a total of 10 pieces. So I got 1, 2, 3, 4, 5, 6, 7 O's and 3 X's, okay? Well, what we have is we have something that's called a mole fraction, okay? So it stands for mole fraction. And to get your mole fraction, just like any other type of fraction, it's going to be the part divided by the whole, okay? So part divided by the whole is how we figure out like fractions. And I want to figure out the mole fraction of O's, okay? So I have capital X here. I know I got X's up here as well. I think you'll figure it out what I'm trying to do. But there's, as far as the O's, there's 1, 2, 3, 4, 5, 6, 7 O's. That would be the part over 10 particles, okay? Which would be 0.70 as a fraction, okay? If I wanted the mole fraction of X, okay, it would be 1, 2, 3. 3 would be the part over the whole, which is 10, which is 0.3. So really, this is like 70% O's and 30% X's, okay? Why is this mole fraction so important? Is that you can use it to figure out partial pressures, okay? So if I wanted to find the partial pressure of the X's, what I would do is take the mole fraction, which is big X, okay, times the total pressure, okay? And if I said that the total pressure of this system was 4.5 ATMs, what part of that would come from the X's and what part of that would come from the O's? Well, I would just take the mole fraction of X's, okay, which is 0.3 or 30%, okay, of 4.5 ATMs, okay, will give you the portion that comes from the X. And 0.3 times 4.5 is going to give me 1.35 ATMs, okay? This would be the partial pressure of the X, okay? If I wanted the partial pressure of the O's, I would take the mole fraction of the O's times the total pressure, and the mole fraction of the O's is 0.7 or 70% of 4.5 ATMs. And 0.7 times 4.5 is going to be 3.15 ATMs. So in this particulate diagram, 1.35 ATMs of pressure is coming from the X's because only 30% of it are the X's, okay? And then 3.15 ATMs of pressure is coming from the O's because 70% of the pressure comes from the O's. And when I add these two together, it equals that 4.15. So how do we apply that to this problem, okay? I told you I'm not going to give you volume and temperature, and instead, I'm going to give you some type of random pressure, okay? So this is a new problem, okay? So this pressure is 3.1 ATMs. That's larger than our last problem that we did, okay? So we have 3.1 ATMs. I want to know what portion of this is carbon dioxide and what portion of this is neon, okay? Well, in order to do that, we need to find the mole fraction of each of them. So if I want the mole fraction of the carbon dioxide, I got to take the moles of the carbon dioxide, 0.1136, okay, and divide it by the whole, okay? So I got to add these two together, okay? And if I add those together, it comes out to be 0.2621. And when I divide these two together, I get a mole fraction of 0.433. I'm going to do the same thing for the neon. What is the mole fraction of the neon? Well, it's going to be the moles of the neon, 0.1485, divided by the whole, which I add these two together, and that comes out to be 0.2621. And then when I divide those two together, I find out that this is 0.5 0.67. So really, 43.3% of this is carbon dioxide, and 56.7% of this is neon. Okay, but these are the mole fraction numbers. Now, to figure out their partial pressures, okay, if I wanted to find out the partial pressure of the carbon dioxide, I'm going to take the mole fraction of the carbon dioxide times the total pressure. And that works out to be a pressure of 1.34 atms. So of this 3.1 atms total pressure, 1.34 of it comes from the carbon dioxide. Let's do the same thing for the neon. We're going to take neon's mole fraction, which is 0.567, and we're going to multiply it by the total pressure of 3.1 atms. And when you multiply those two numbers together, you get 1.76 atms. So you're getting more pressure from the neon. And remember, that's because there's more moles and hence a larger mole fraction. In fact, 56.7% of the pressure comes from the neon. So you're getting 1.76 from the neon and only 1.34 from the carbon dioxide. So this is a way that you can figure out partial pressures without ever having volume and temperature. You're just going to have to use mole fractions, okay? And then you're multiplying those mole fractions by the total pressure in order to get your partial pressures, okay? And if you found this information helpful, please give it a like and subscribe. Even adding a comment will help push this information to other students that are interested in learning chemistry.